Hello everyone and welcome. So before we get started with breaking down all of the different types of simulations that we have in Houdini, I wanted to just show you an example of all the different types and just discuss a little bit about them so you know basically kind of what we're going to be tackling. But then also, if there's a couple of terms that you might come across when maybe discussing effects with someone or looking on forums, maybe looking through the help files, you probably come across some of these terms. And if you haven't done simulations before, some of them might be quite foreign. So I want to sort of break these down now, because then as we move forward, you'll kind of have a better understanding of what we're talking about as we tackle each of these. Now, we're not necessarily going to be looking at every single one of these. For example, the sort of FEM solver stuff, we're not really going to spend too much time on. But we're basically going to cover most of these in some way or another in this course. But we'll keep it as basic as we can, the most basic version of each of them, so it's not overwhelming. More than anything, what I want to equip you with in this course is an understanding of what the different types of effects are and how to set them up or how to get started so that you can at least get the most sort of basic version. Okay. In order to obviously get much better at simulations, you're going to need to practice and learn much more advanced courses, and that takes time. But here I want to break it down in a way that it's not so foreign or so difficult to kind of reach for. So yeah, we're going to just tackle the basics essentially. So the first sort of group we're going to look at over here is the particle simulations. So if you hear me talk about pops, it's like how Houdini likes to name everything with an op at the end, or at least they used to. They seem to maybe be moving a little bit away from that now, but in the beginning there was such thing as pops, right? Particularly there was a pop network, which used to be a little bit different, but now it's basically just a dot network that already has some pops set up inside of it. So if you see that, if you hit tab and you see that, it's just a shortcut to get to some particle simulation. So it's basically just particle operations. In other words, nodes that do particle simulations, right? So it's just a simple particle sim. It's all about taking single points that are separated from one another and simming them like that. And the interesting thing, or one of the most important parts of pops, is that the particles are not intrinsically aware of one another. So they can, although they are, they could be infinitesimally small, like, tiny little particles, but even if you gave them some sort of size, they can go through one another. They don't bounce off of one another, collide or anything. They just go straight through one another, and they're not aware of each other. They can be made aware of geometry like we have over here, but not of each other, although we can make them aware of one another, but that's an additional step. Okay, and that adds heaviness to it. So one of the benefits of the particle sim is that it can be very light, and actually them not being aware of one another allows us to do some cool techniques like wedging in order to get more particles than we would probably ever be able to handle in a single simulation. So there's a lot of cool tricks that come with that, but it's just important to note that. So we're just simulating particles. We can give it things like gravity or give it collision objects, and they essentially are just free-flowing particles. So that's probably the most basic simulation, and it's definitely the first one we're going to start with. But then a little later in the course, we're going to tackle two other types of pop sims that are actually a little bit more advanced. Grains, for example, which is often used for sand and sort of dirt simulations, but can be used for a much more wide variety of simulations, is really just a pop sim. But it's a pop sim with constraints. And constraints are essentially just lines, polylines that are drawn from one particle to another in order to tie them together in some way, whether that is restricting them from moving too far away from one another, or restricting them from getting too close to one another, or applying different forces to one another, maybe a rotational stiffness, or there's lots of ways that we can apply these constraints, but they're essentially just rules or kind of glue that binds these particles together in some way, but we can get quite fancy with the type of constraint, right? So for example, with this grain simulation, these particles actually have a size. Now that is just sort of the way it's represented in the viewport. You could actually just remove the sprites that are copied onto these and it would look like this sim. But the thing is, they have a sort of a force that prevents them from overlapping like the particle sims do, like the pops do. So if two particles collide, they actually have a radius and they will not penetrate or cross the same space. But then there's also constraints that are preventing them from spreading out too far from one another, and those constraints have certain kind of strengths to them. So if we had to hit this with a big collider, of course we can pull those grain particles apart from one another. But there's a sort of because this is meant to be like a wet sand simulation, there's a sort of a soft constraint keeping those particles together. So if you hear or sort of come across the grains sort of simulation, just don't forget that it's not a whole thing on its own. It is basically just pops, but with constraints. Okay. Now, in a similar way, pop fluids is still just a pop sim, but with an additional node inside that allows or sort of forces the particles to be aware of one another. Not in the same way that grains does, where it has an actual constraint network, but in a way that it has forces that pull them together and also push them apart. But it's not one particle tied to a very specific other particle or a network of particles. It's a radius. It's kind of like a proximity check. So it just looks for any particles that are near it and applies this kind of outward and inward force to keep it moving how we would expect a fluid simulation to move. Now, it is not quite as good as doing something like a flip simulation like we have on the right here, but it does help give us that sort of droplet look. So a lot of the times we'll use pop fluids for creating little splashes or maybe rain or things dripping down, but without doing the full-blown flip simulation, because sometimes this with the flip, in order to get small kind of droplets like this, like here you can see it kind of is grouped together a little like water. To get that with flip can be a little bit difficult because of the way flip works. So using a combination of these two can be very powerful, right? So again, it's just a pop sim, but it has some additional forces, and that's really it. Now, while we're talking about these particles, we might as well move over to our water simulations. But actually, in order to explain this, we need to discuss these smoke sims at the bottom. And the reason for that is because a flip sim is essentially a combination of particle sim and then a fluid simulation, right? So let's talk about these first. So a fluid simulation, now when you talk about fluids, you often think of, liquids, but a fluid is really, gas, right? Because a gas actually moves like a fluid. Liquids and gases move in a very similar way, but they're just different densities, different temperature, right? So the reason we sort of use this fluid simulation, in other words, with the same algorithms that we're using to move the gases, we apply that same thing to when we're moving liquids over here, but just with different settings, and it gives us these liquidy kind of motions. So within fluid sims, we have a standard sort of smoke simulation. So we have a smoke solver, and then we have pyro. Now, the difference between these two is just the number of different fields that we have to play with. The smoke simulation really just has a density and then temperature, right? We can have other forces in there as well. We can have divergence and a couple of other things, but really it's the most simplified version of a fluid simulation, in that we have one field that is represented or rendered, but then we have another field that is affecting it. So we've got the temperature, and of course we would have our velocity field as well, so that it's obviously tracking the motion of this, and we would use that for motion blur. Okay, So this is just emitting one fluid, essentially. Whereas the pyro works on basically it essentially has multiple fields, and they have this weird kind of relationship between one another. So we have fuel, which is, that's exactly what it sounds like. There's a field that is similar to density in that it just has sort of, values. So they would be sort of 0 to 1, or it can go higher though, like 0 to 10 or whatever. But they just store these kind of, positive values of where there is fuel. And that field is usually left invisible. But what happens is there's a sort of a temperature threshold where that fuel will ignite. Okay, so we can set that threshold and decide how easily combustible that fuel is. And then we have our temperature field, which again is also invisible. But if the temperature field in a particular voxel is a value that is higher than the temperature threshold that we set, and there is some fuel, then it will ignite. And when it ignites, it creates a heat field, which is essentially just a temporary field that tracks where things have actually burned in this frame. So essentially it is the flames itself is basically the heat field, right? But when it combusts, of course, it spreads. It creates some density, which is actually the smoke. So, if it's a smokeless fire, it doesn't do that. But if it is a fire that has smoke, it will create density, so that gets advected by the same velocity and temperature. It releases more temperature, or at least it spreads out the temperature that caused the ignition. And then it obviously has its own velocity and things like that. So it kind of forms this chain reaction where as it almost explodes and pushes outwards with heat and temperature, then that temperature will ignite more fuel, which creates more heat and temperature, which spreads. And so it essentially acts like you'd expect fire to if there was some fuel, right? So here we have our rubber toy that is just essentially filled with fuel, and then at the base there was just some temperature. That's all I used to create this simulation, is just some fuel and temperature, and then it creates all the rest, right? Because it just ignites and then spreads and then creates the flames and then the sort of the smoke sim and everything. Okay, so it is based on the exact same principles, but there are just a lot more fields at play, and they have a very sort of distinct relationship between one another. And that, like I say, this chain reaction of one affecting another, which affects another, and it kind of causes this loop, right? Now, we have spoken about dense volumes when we discussed volumes, and both the smoke and the pyro solver are using dense volumes. So we have to set up a container, and then it will only simulate within that container. We can expand that container as the fluid moves, but then we have to be very careful that it doesn't get too large. And we are storing values in the empty voxels for every field that we have. So actually that's why pyrosims can end up being really, really heavy, because we've got, sometimes up to like 7-10 different fields, all dense fields being tracked for this one simulation. So we need to be a bit careful with pyro. However, there is a new relatively new simulation, which is sparse pyro. So that is a pyro simulation, but it is based on sparse volumes, so like our VDBs, right? So it has an actual active field where it then looks at those voxels and treats them and fills them with values, but beyond the active field, those voxels are not calculated. So it tends to be a lot more efficient. The look by default comes out very different. Of course, we can work with both of these. None of these simulations have been worked with much at all. They've just been essentially default, like what you'd get off the shelf, with maybe 1 or 2 little tweaks just to make it look a little better. But we would want to work with these a lot more. I mean, this pyro looks very low res, but there's a lot we can do in the shader to make it look better. And the same way that sort of the difference between these two can kind of be compensated for if we had to work with them both. So They will always look probably a little bit different to one another, but if you work with it, you could get whatever look you wanted. So if you wanted this very big fluidy sort of burning, then we could get that look in the sparse pyro, but we would just have to work with the settings. Okay, so now that we know how these sort of fluid simulations work, the flip sim over here is essentially a combination of pops and fluid sim. It has invisible fields that are controlling things like pressure and temperature and velocity, and storing these sort of values in a fluid simulation, right? But the pops, the particles that are advected by that, so and advected means essentially moved by it or sort of affected by it, right? The particles that get moved also help store bits of information that are very difficult to store inside of a fluid simulation. And also the particles are the main, essentially the point of this flip simulation. These are what get meshed and turned into an actual solid kind of body of water. So what we essentially do is we have particles, but then the particle velocities and all the attributes on it are converted to fluid simulation, but it's invisible. That gets advected and have a pressure applied to it. They do all of these kind of calculate non-divergence, and there's all these kind of calculations that we do on the fluid. And then whatever calculations happened on those fluids, the results are sort of pushed back onto the particles, and the particles are advected by it. And then on the next frame, we go from particles to fluids, and then fluids back to particles. And so that's the kind of loop we have every frame, so that it gives us this kind of look where, although there are separate particles that are not actually aware of one another, they can go through one another, same as the pop sim, but they seem to move as one big kind of body. There's these kind of cohesive and adhesive forces between them, because once it gets converted to a fluid sim, now these voxels tend to sort of move in a way that they're almost aware of one another, and then that result is projected back onto the particles. So that's why we end up with a flip. Okay, so basically flip sim is just any kind of a liquid sim, and we can get it to be very viscous, so we can do mud, or we can do flip fluids of different densities, so you can have that kind of like ink in water or oil in water look. There's lots of cool things we can do with this, but that's just a basic flip simulation. Okay. Oh, and we do have an ocean simulation as well in Houdini. The ocean is basically just a sort of a procedural displacement map that, based on sort of wind and choppiness and everything, we can create this map. But there is a way, which is actually what I've done here, which is to take that displacement map that's just on a grid and then project it onto a flip tank, which then has these liquids moving to match and follow that ocean sim, but then it also simulates. So around this character, it would move, according to the character, but then at the edges we could blend it back in with the rest of the oceans, which is just a displacement map. And so we have a very light way of calculating a sort of a simulation in the middle of a vast ocean. Okay. And then also here having objects actually interact mutually with the fluid, where the fluid bounces off of it, but it kind of floats in the fluid. This is actually something that is surprisingly difficult to do in Houdini. Well, actually, it's not difficult, it's easy, but it's surprisingly hidden. And it's something that a lot of people struggle with. It's quite a common question, and the answer doesn't seem to be very forthcoming. So in this course later on, I'm going to show you a little example of how to do that, because it is something that a lot of people end up wanting to do at some point. And then when you start searching for it, the answer is kind of difficult to find. So I'm going to solve that for you. All right. Now the whitewater simulation is essentially just a step further from the flip. Okay, so it's based on a flip simulation, but it kind of uses certain information that's happening in here to calculate whitewater, which is just essentially particles, additional particles that are simulated to follow the surface of this liquid or to be underneath or outside. Okay, so there's three types of whitewater. There's spray, which is essentially above the surface, outside of the liquid. There's foam, which is on the surface of the liquid, and then there's bubbles, which is underneath the surface, right? Now you can treat them as actual bubbles, but really the main thing is to turn that into a volume so you get that kind of white churning. In other words, those very tiny bubbles that would be created when someone jumps into the water. To get the proper bubbles that kind of stick together and rise up, you'd want to maybe use a different simulation. So to get really realistic water simulations, you generally have to layer things up quite a lot. You've got your 3 different types of white water, you've got your flip, you might even have pop fluids combined with that to get some splashing, and then you'll have a bubble simulation under the water as well, which would just basically be particle, like a pop sim as well. So lots of layering to get very realistic water. Okay, so this essentially just we define certain variables about this this flip that it's based on. So, for example, how easily should the bubbles be created based on a difference in curvature or a difference in velocity or whatever, and then it will create essentially in those areas where there's like so like here, as the wave kind of rises up, there's a little sort of splash. In that area, there would be very high area of changing velocity, and so that would be a source for the white water. It would create a lot of particles in that area, and those particles are fed into the white water simulation. And then the white water simulation uses the original flip sim and uses the surface. Now, when I say surface, I mean it's a field. But remember when we were calculating SDFs, so a VDB, where you can see the sort of surface, but it's actually a volume that's hollow on the inside and outside, but actually it has negative values on the inside and positive on the outside. Well, that's a surface, okay? So the flip sim has essentially an invisible surface field that it's calculating. And you can actually see, you can literally see the surface of this liquid. Well, that's how it's figuring out where it's inside or outside. And the white water uses that to figure out, okay, I should now float on the surface because I'm foam, but then other particles get sprayed out and they will make sure they stay above the surface. But if they go into the surface, they die. And then the bubbles remain below the surface. And if they touch the edge of the surface, then they die. Okay, so that's a white water simulation. And then we have this section on the bottom left here. These are essentially our soft bodies and our rigid bodies. Okay, so that's just different ways of moving geometry, but with certain constraints or settings. So Vellum is quite a diverse simulation. It's actually, for the most parts, has sort of been replacing the wire sim for hair or actually for wires. There might still be the occasional need to still use the wire sim, but Vellum is generally how we would simulate hair now as well. So it can be used for thin lines like a wire, but it also can be used for cloth and even for sort of soft bodies like this fem sim over here, where it's kind of like a soft mesh, but it actually maintains its volume on the inside instead of like here on the left. This is just a cloth sim. Okay, so this is not trying to maintain any volume. This is literally just completely hollow and allowing it to flop like a normal cloth sim. But Vellum can do this, in fact, both of these types, right? So Vellum is probably what we're going to mostly stick to because that is the newer version. It is much better, but there may still be occasional uses for these other two, so it is worth talking about them. Fem, it's a finite element methods, right? This basically uses a method of filling a volume with like a sort of a tetrahedron kind of lattice, really. And it's using that to maintain volume or sort of define how things should move and bend, right? So you can use Fem for cloth. You can even use it for wires. It's also sometimes used for fractures, like on the bottom here. But if they wanted the fractures to be a little bit maybe softer. So, for example, if there was some kind of explosion and there's like chunky bits of meat or whatever, you like blow up an alien or something, you could use Fem for that. But at the same time, you could also use Vellum. So it's really up to you. There's just two different solvers that do a lot of the same thing, but in a very different way. Right. And then a wire sim is exactly what it sounds like. It basically just simulates long, sort of poly lines, but you can give them width and you can give them stiffness. So, stretch and compression stiffness, and you can give them a rotational, so angular stiffness as a way to try and make it so is it like a very rigid kind of like this is almost like a hose pipe sort of thing where it's got some rigidity to it, but it could also be, you could make it look like sort of wire cable that's maybe really, really thick and doesn't, like, it resists bending a lot. Or you could have it be like hair, which it just, would bend super easily. Okay. There are some issues with the wire sim. It's not honestly the most stable simulation, especially when it comes to resisting stretching. You can have it resist a little bit, but if you wanted something like, for example, hair does not stretch. Okay, it would snap, but it just does not stretch. It can bend and flop around easily, but if you pull it, it just snaps. And that's basically where the wire sim struggles a lot. Okay, it basically the higher you push the stretch stiffness, it starts to look weird before it ever stops stretching. So you have to do a lot of tricks to try and get it to not stretch. So I wouldn't recommend this highly, but occasionally you do still need it. So, it's good to know how to set it up. And in fact, it's probably one of the easiest sims to set up. All right. Then rigid bodies. So there are two different types of rigid bodies that we're going to be looking at in this course. So bullet and then RBD. Now, technically, bullet and RBD can do the same thing. So we could simulate a Voronoi fracture like this using RBD, and we could use bullets to just have a normal object move around. But bullet is basically using, like predominantly wants to use a convex hole. So just like a sort of a simplified shape that encompasses the volume of each of these particles, and it tends to be a much lighter simulation. It's really, really useful. Occasionally there are some issues with it though if you have very complex geometry. So a lot of the time, if you want something that's more complex like this, you would actually break this object down into individual pieces. So its arms and its legs and each of these sort of spikes on its head will all be separate objects. Maybe even here, because there's between the neck and the body of the toy, there's a strange kind of bend. You'd separate the head and the body and then glue them back together so that each of those separate pieces is its own convex piece of geometry. Then that will simulate well in bullet. But RBD tends to be, so it's a volume, it uses a volume method for collisions. And so it can handle much more complex geometry when it collides. But it does tend to be a little heavier, and that's why by default we actually use bullet most of the time. Even when we drop down a rigid body solver, it's got the two different modes, but predominantly it'll be set to bullet first, and we'll use that as much as we can. Okay, but occasionally we will flip between them depending on what we're trying to do. Or if you're running a sim and it doesn't look like it's coming out well, you can always switch to RBD. But we also do, when we calculate collision objects, like here in the vellum, there's a collision object here, or inside of pops as well, there's an object here. In whitewater here, I had this object being just a static object, so it is collided with but is not affected by the water. So all of these three are an example of where there's a collision object, and that collision object would be calculated with an RBD simulation so that it's using the volume of the object. But bullet is really good for things like when we do a Voronoi fracture. And if you haven't come across that term yet, Voronoi is just a sort of an algorithm of sort of determines how to break something up into these sort of cellular shapes. And we use that as a way to essentially pre-fracture objects into little chunks and pieces. We glue those back together with constraints, but then we can break those constraints based on forces. So here you'll see at the bottom it fractures first, and then the rest of it fractures, because I used deliberately some very soft, like weak constraints over here so that this does not simulates to well, so that it's not too rigid and that it actually falls apart. But if I strengthen those constraints, then this would just hold together very well. And that about wraps it up. So these are the different types of simulations that we're going to be covering. We may not really talk about FEM that much. We're mostly going to focus on Vellum for that type of soft body simulation. But it's good to know that all of these exist and what these terms kind of refer to, and what these are. So if you see in the tabs as well at the top here, you'll kind of start to recognize these sort of names and understand what they do. Okay. So thank you very much, everyone, and I'll see you in the next lesson where we'll be talking about actually setting up our particle simulations and what simulations really are. Okay.